Okay. So let's get started. So there are 7 guided problems and 8 practice problems that you will do. The first practice, the guided example is to look at the analytic solution of ODEs. So when you get a very strange ODE in your classes, how do you do? How do you find the solution of it? For example, when we look at this nonlinear ODE, so it asks what is the order of the ODE? The order is first order. It's nonlinear because it has a sine and divided by t, and the ODE is homogeneous. So we use Wolfram alpha to find the general solution of the ODE. So we go to the Wolfram alpha and then type in the equation for this. This is dx dt is equal to 5 times sine of x divided by t. You can get the general solution of the ODE. So here it says x of t is equal to 2 times arc cotangent constant divided by t to the 5th. But in this case, we have an initial condition of x of 1 is equal to 1. So if we want to add that, we can type comma x of 1 is equal to 1 to get the particular solution. And this is a particular solution. You can also solve it with on your own. So you have the general solution, you have the initial condition, you can solve for the constant, which turns out to be cotangent of 1/2. And you substitute in, you get the particular solution. Well, this problem asks you to plot this analytic solution, but when you input it into Python, you need to realize that we don't have cotangent or arc cotangent functions. So you might need to use trigonometric identities to convert cotangent to tangent, which we have in Python. So you will be using these 2 identities. And since these are plotting, you already know how to do this, so I won't go over this. So the numerical method for solving first order ODE starts with the very simple form of having a first order derivative equals to something that's related to the independent variable x and the dependent variable y. And we want to numerically solve it subjected to some initial condition of y of 0 of equals to something. So we want to first realize what are the knowns and what are the unknowns. So we know the independent variables at different time steps. So x of I, x of I plus 1, all of those are given. And we are also given a constant step size delta x. We also have an initial condition. So the original function evaluated at the first time point or first initial independent variable is already given. And we know the function, the derivative function given in the ODE here. But what we don't know is the original function's form. We don't know that. And we also do not know the original function evaluated at the next time step because the original function is not known. And it's important to note that in all the theories that in this lab, we use x as the independent variable and y as the dependent variable. But in reality, you might also see other variable names. For example, you can use t as time as the independent variable and use x as the dependent variable as position. So you need to distinguish between those to avoid confusions. The forward Euler method is the simplest method that we can solve ODEs numerically. It takes inspiration from the forward difference approximation that we learned in the last lab. So the forward difference approximation gets from the approximation of the definition of derivative. And if we rearrange so that we get y of xi plus 1 to the left explicitly, we can get the y of x plus y prime of x times delta x. And this should be very familiar to you if we look at it geometrically. Let's see if we can draw this. Let's see this, okay. So I have x and y. And the forward Euler says that we have the function y of xi plus 1 is equal to y of x of I plus the derivative at x of I times the step size delta x. So if we have the graph, we label this as f of I, the initial point, and some x of I plus 1 that's separated by delta x, then what we already know is the point at which it is x of I and y of x of I. This is the initial condition, the IC. What we also know from the ODE is that we have some kind of derivative is equal to function that's a function of x and y. This is already known. So we can evaluate it at this point and then get a derivative. And what the forward difference does is that we have the initial point, the IC, we have the derivative, the slope, and we'll just multiply by this interval so that we go from here to here. So this is our second point. So this is y of x I plus 1. So basically, it's just one basic step. This is from the slope formula. And this is called the forward Euler method. And because we know everything on the right, we can simply compute this for different loops, and we can loop it through every step. And because we know everything on the right, we can explicitly evaluate this. So this method for Euler is also an explicit method. Any questions? Okay. So I'll go through one example for forward Euler, and you can try it on your own with the practice problem. So here we have an ODE that we can define in Python as dx dt is equal to, and do a lambda function, and the independent variable here is t. The dependent variable here is x, which is important to distinguish from all the theory above. So because independent is time t, dependent is x, we have 5 times sine of x divided by t. So here we define the ODE. We have the initial condition x of 1 is 1. So we can say x0 is equal to 1. On the domain of t is in 1 to 3. Let's say t minimum is equal to 1, t maximum is equal to 3. And we can define t as since we have given a step size of 0.1, we can use a range, NP a range, starting from t minimum, ending at, but not including at, t maximum at the step size. So we can define dt as 0.1. So the step size is dt. But since we want to include 3, so if we print this, it doesn't have 3. So what we can do is to add a dt here. So it includes the endpoint. Okay, so here we have defined the t, the time. So I'll also, for convenience, define the length of t. So t length is the length of t. And you can print it out. T length should have 21 points. Okay, now we want to solve this ODE using forward Euler's equation. And to do that, we'll need to construct the forward Euler algorithm. And for that, we need to look at the equation. The equation is here. So y of x I plus 1, in our case, is x of t I plus 1. So we have x of t, x of I plus 1. So t is already ingrained in the index. I plus 1 is equal to x of I plus the derivative, so dx dt, evaluated at x of I, x of 1, x of I. And then because this derivative takes t and x, so x is the second input, and the first input is t, and t should be t of I, multiplied by the dx. And this will be the forward Euler implementation. And we want to loop this through all the time steps. So for I in range, the length of t, so t length, we will go through this loop. But if you run this, it will give an error because we haven't defined x yet. So we need to define an empty x. So we can start off by defining x with all zeros. So np dot zeros of what size? The size should be the same as the length of t. Zeros. Okay. And then we haven't defined dx because it should be dt. This is out of bound. Let's see. So I is at 20 and the length of t is 21. So this is I plus 1, this is 20 plus 1. So it's one more. So what we need to do is to minus 1 in the range so we don't get out of bound. So now we have found out x. Okay, so x is all 0. That's not good. So what happened here? So because we initially defined x here, so if we print x here, it's all 0, right? And then we go through the loop, it's still all 0. Why is that? It's because we haven't put the initial condition in. The initial condition is that when it's at the beginning, it should be 1. But the beginning here is 0, so it's adding on zeros. So what we need to do is to define the initial condition. So x of 0, the 0th index, is equal to 1. So this is defined initial condition. Now if we look at it, if we print x, we have initial condition of 1, and this is to be filled out. And through this forward Euler method, it starts to get the solution. And without plotting, we don't know if we actually solve this correctly. So we want to plot the forward Euler solution. So let's plot that. So fig x is equal to plt dot subplots. Okay, we have an axis. So x, we want to plot the independent variable t, and then the dependent variable x. Okay, and this looks quite reasonable. And we can label this as the forward Euler method. Then we can do some adjustment and label it with x dot set x limit as the minimum of t min to t max. And then set the y limit as it starts from 1, we can from 0 to 3.5 maybe. Okay, to 4. And as always, we want to label the x and y axes. So the x label is t, the independent variable, and the y axis is x of t. And you can double check with the below. So this is for Euler. And it wants us to compare the solution with the analytic solution. So the analytic solution we should already get from the first guided problem. So the analytic solution is this. So we'll just copy this and then paste it in. So we want to plot the analytic solution. So t comma x exact evaluated at t exact. And now we have also the analytic solution. And we'll also check if we have followed the guidelines. So for Euler solution with solid markers connected by dash line. So here we can put solid marker, which is O, and then that dash line is 2 minus sign. Okay. And this we have plotted for Euler and analytic solution. So we'll see the for Euler method has some kind of error compared to the analytic solution at this particular step size. So it's getting the solution in bulk, but it's not quite accurate. But we'll see there are more accurate methods later. So let's try the practice problem out with also some chemical engineering background in it.
See.
Okay. The forward Euler method should be quite straightforward to understand because it's just a rearrangement of the definition of derivative. But what's more complicated will be backward Euler. Okay, does anyone have question on the practice problem? Okay, cool. So the backward Euler's method takes inspiration from the backward difference approximation with a constant step size. So here is the backward difference. It's basically assigning the same thing, but to x of I plus 1 instead of x of I. So if we rearrange this y of x I plus 1, then we'll get this expression. And because the derivative in the ODE is not only dependent on the x independent variable, but also on the dependent variable y, so we can also write it in terms of this. But if we look at individual components, we know the initial condition, we know the step size, we know the independent variable. However, we do not know the original function evaluated at the next time step. So this is an unknown. So we have an unknown on the right-hand side, so we cannot evaluate this explicitly. But if we look, we know everything else except for y of x plus I plus 1. So we have that both of those on the left-hand side and also right-hand side. So this basically becomes a root finding problem. So if we move everything on the right to the left, we'll get this equation. And then we will redefine the variable that we don't know, the y of x I plus 1 as z. And we get a function g of z is equal to this. And now everything will be known except for z. And we can solve for z using root finding algorithm that we went through in lab 1, either through bisection method or Newton's method. But to keep it simple, we can just use the SciPy optimize.root. If we look at that documentation, basically we need the function that needs to be solved, or the g of z that we defined, and some initial guess. And the initial guess can be very simple. We can guess x of I as an example. And because we don't know everything on the right, we cannot solve it explicitly. So this method, backward Euler, is an implicit method because we're solving for a root finding problem first. The advantage of implicit method is that it's more stable than explicit method, but it requires to solve a root, so it's more computationally expensive. So let's do a guided problem. So basically, this is the same ODE. So I'll just copy and paste the ODE definition part and the exact solution. So the hard part is to look at the backward Euler. So the time step you can also copy down, and the exact solution you can also copy down. But the different part is backward Euler. Before we code it up, let's actually look at its geometric interpretation so that we understand what's going on in backward Euler. The backward Euler's method is y of x I plus 1 is equal to y of x of I plus y prime x I plus 1 y x I plus 1 times delta x. So we have an initial x of I point and a final x I plus 1 separated by delta x. So as usual, we know already this is the initial condition. So at x of I, we have some y of x of I. So in forward Euler, we have something like this. We already know the slope at the initial point, but here we don't. What we're using is the derivative at next point. So we know the derivative at this point, but we don't know where it is. We don't know if it's here, 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 or here. That's what we want to determine. So we only know the slope field. So basically, we're given a slope. And then this slope, we'll need to move this slope. So we'll move the slope to see whether it's up here or below. So basically tracing the slope back such that it starts at the initial point. So we already know the slope, and then we'll just copy the slope to here, and then let it go through a full step, and then find the backward Euler. So initially we know the slope in the beginning point, but in this case, we only know the slope at the ending point. So we're tracing back the slope. That's why it's an implicit method, because we don't know the value at the next point. And so to implement it, we will use the definition. So the independent variable is t, dependent variable is x. So x of I plus 1 is equal to, the formula is x of I plus the derivative at x of I, which is I, t of I, and x of I plus 1 multiplied by dx. But note that we already said that we do not know this whole thing. So we need to solve for y of xi plus 1. So to solve it, we need to use this root finding algorithm. So scipy.optimize. So we can copy this. And also import scipy. Okay. And then for the root finding algorithm, we need to define the equation. So the equation g of z, g lambda of z, what should it be? So it should be z minus y of x of I. So z minus, in our case, is x of I minus the derivative evaluated at t of, evaluated at t of I plus 1, comma z times dx. So this is our g. And our initial guess can be x of I. We'll import scipy at the top. And the dx should be dt, because t is the independent variable. Okay, and this is the result of the root finding algorithm. And we are interested in the x, which is the result. So since this is a dictionary, we can access it through dot x. So we get everything within the x. And then we only want the first value, so x of 0 index. And this is the root that we have found for this iteration. And this root finding algorithm should be placed before. So we have defined g, and then this whole thing we already solved for. So x of I plus 1 is equal to the root finding algorithm. So we need to do this for I in range t length minus 1 to avoid overflow. And then we have solved for x through backward Euler. And we can also plot this to verify if it's similar to before. It's very similar to before. So fig x is equal to plt.subplots. And the axes plot this with markers, dashed line. And then you can also plot the analytic solution. So t and then x exact evaluated at t. And then label those. It's backward Euler. And the analytic. and you can perfect your plot yourself. But let's go through this code again. So the important part is to first define your ODE using a lambda function. And the lambda function takes in an independent variable and a dependent variable. And you define the different time steps with your left bound, your right bound, and your step size. And then in the backward Euler method, because we do not know the y prime at I+1 location, we have made this problem into a root finding problem here. So we make this part unknown as z. So we want to solve for z. And z is exactly what we're looking for y of x I+1. So we need to input this line into the code. So we defined a g function, g lambda function as lambda of z, z minus x of I, which corresponds here, minus x dy dx. So dx dt, t at I+1, comma z. Like here, multiplied by delta x. In our case, it's delta t. And then for each iteration, we will solve the root finding algorithm and then find the result and update it. And we get the backward Euler method. And then you can try the backward method using the practice problem. This one, so we need to change one of these. This was oh yeah, it's fine. Either way, it's your. Okay. Okay, I just didn't explicitly write these three things out. So how do you define see how this is like see inside do something.
What do you get for the lunch? I didn't even do it. Yeah, this was this is number. Yeah, I did two. It looked like this. Number one. Yeah. I didn't. Good job. Oh, God, there. if I have class all the should my kind of should. Yeah, no, but the end of at the end of this learning,
Okay, the forward Euler and the backward Euler method each are explicit method and implicit method, and they're all first order method, and we call them first order because of their relationship with the error that they have. We'll discuss error analysis in later labs, but here we can look at the midpoint method that takes inspiration from the central difference. And what it does is that it takes a half step of forward Euler. I think to illustrate that, we're best to look at a problem. So here, same as before, we have x of I, and then with the dx separation, we have x of I plus 1. So what midpoint error method does is that we already know an initial point of xi, y of xi, and then we know already the slope. So what forward Euler does is that it goes directly to the xi plus 1. But instead, the midpoint method, what it does is that it only goes to half the step size. So the half of step size is x of I plus delta x divided by 2. So it goes here. And at that point, it evaluates the derivative again. So it finds another slope. So let's say this initial slope is k1, and then the other slope is k2. And what it does is that it uses this k2. So let's say slope k2 is here. So I move this k2 to the initial point again. Approximately, this is k2. And I use that k2 to do a full round of forward difference. So this is the midpoint method. So initially, if we just do the k1, one full step, this will be the forward Euler method. And instead, it takes a half a step, looking at its k2 slope, and I use the k2 slope to do a full step as the midpoint. So this decreases the error. So from here to here. And then for the guided problem, again, it's the definition of ODE, the exact solution, and the time steps. And the important part is the how do we define the midpoint method. So again, we want something to contain our results. So let's name that x of midpoint of the size of the length of t. And then we define the initial condition. So midpoint, the initial condition was x of 1 is 1. This is the initial condition. And then to start the midpoint method, we do a for loop for I in range t length minus 1. We'll calculate the k1 and k2. So k1 is equal to the derivative evaluated at the first point. So the derivative is dx dt, evaluated at the x of I, the initial point, and y of I. So in our case, it's x of I. And k2 is equal to the derivative evaluated at the midpoint. So same thing, derivative, but in this case, the x-axis, which is t, should be initial point plus the t minus 2. So it's at the midpoint. And we also evaluate the y, which in our case is x, as plus k1 multiplied by dt divided by 2 using this equation. Now, after we have k1 and k2, we can do this iteration step. So x of midpoint of I plus 1 is equal to x of midpoint of I plus k2 times dt. Oh, and p dot zeros. X of midpoint int. Okay, here the initial condition should be the list indexed at 0. Okay, now we have x of midpoint. And then we can plot it as usual, and we can get the midpoint method. Something's off. Oh, here the x should be x of midpoint. And then the best way to check if your answer is correct is to plot it against analytic solution. If it deviates from the analytic solution by a lot, it's probably wrong. But if it matches, it's probably right. Okay, and then keep doing the practice problem with the midpoint method. Let's see. Basically, but it's not the so we need to do this change it comes to The last algorithm that we'll introduce is called fourth order Runge-Kutta method, and it's by far the most accurate method. And it should give very, very close to the analytic method, even if the step size is pretty large. And it's a lot of text to read, but I'll just show it with the graph. So because it's fourth order, it does a lot of computation. So initially it gets from x of I to x of I plus 1. And the distance is delta x. And so the middle point should be x of I plus delta x divided by 2. And the RK4 method says that, okay, we initially have some point. The initial condition we already know at y of xi. And we can get some initial slope called k1. This we also can know. When it does that, it starts at the beginning point, do a half step of forward Euler. So it gets to the midpoint here. And then record the slope here. So maybe the slope is like this. So the slope here is k2. And then we use this slope k2 back at the beginning point. So let's remember this slope and then draw it here. This is k2. And using this k2 slope, we then again do a half step of forward Euler. And then maybe the slope is like this. And record that slope as k3. And then with that k3, again, we go back to the beginning and then record that k3. And then we do a full step of forward Euler. We go to here. And then we record the slope again. So maybe the slope is like this, k4. And then finally, we take the weighted average of k1, k2, and k3, k4. So the weighted average is 1, 6, K1 plus 2 of K2 plus 2 of K3 plus K4. So you're basically taking 1 plus 2 plus 2 plus 1. So that's why you have a 1, 6 here. So you take the weighted average, let's say this is K5. And then the weighted average, maybe it's, let's change the color. Can I? I don't know, here. Let's say the K average, so it should be focusing more on K2 and K3. So K2 and K3 are here. So maybe the K4, the K5 is like this. And then you use K5 to do one step of forward Euler. Like this. And this is the RK4 method. Basically, it takes a lot of different slopes and taking the weighted average to do one forward Euler. So it should be very accurate, but the downside is that it requires a lot of computation to find these slopes. So there's a trade-off between the computation time and the accuracy of this method. And to code this up, again, the ODE should be the same. The time step should be the same. It's just the algorithm will be different. So similarly, we still define the RK4. So we fill it with zeros as placeholder. And then we define the initial conditions, RK4 of 0. The 0th index should be the initial condition, which is 1. And then for I in range of t length of -1, we do our RK4 implementation. So we look at back, you should have K1, K2, K3, K4. See if I can new view. Okay. Okay, so K1 is equal to the derivative, which is dx dt, evaluated at x of I. So in our case, its independent variable is t. So t of I, comma, y of xi. In our case, it's x of I. And then K2 is equal to dx dt, evaluated at t, but plus a half step size. So that is dt divided by 2. And I also evaluate at this part. So x of I plus K1 multiplied by dx, or in our case is dt, divided by 2. K3 is equal to dx dt evaluated at, so this part is x plus half step size, copy and paste, and evaluate at x of I plus K2 multiplied by dt when divided by 2. K4 should be dx dt evaluated at x I plus 1. So in our case, independent variable I plus 1, and then dependent variable, which is x of I plus K3 times dx. Now we take the weighted average of everything. So we have x of RK4 of I plus 1 is equal to RK4 of I plus dt divided by 6 multiplied by the weighted average, which is K1 plus 2 times K2 plus 2 times K3 plus K4. Okay, let's hope this runs. Okay, so I plotted, I have dx. Instead, we should have dt because that's our independent variable. Okay, so now we have our RK4 and we can plot it. Okay, there's something wrong because it has deviated from the analytic solution. So visually, we see that our code have something wrong. So where is it wrong? X. K1 plus dt divided by 2, K2 dt divided by 2. Let's see, compared to the solution. Oh, I used x instead of x of RK4. So I should have used the RK4x because I have used x in different other places. So be consistent in your namings. And then you'll get the RK4. That's exactly lying on the analytic solution.
Yeah. Thank you. It's a thought. I was a little confused. I thought that would be. Something. I don't think we were ever given a T0. We just want to T00. Yes, 100. Thank you.
So the minimum control is this is alpha divided by this is SciPy has a built-in solver called solve-IVP, or solving for initial value problems. So it requires a function that's our ODE, and then T-span, which is the left and right boundaries for the independent variable, y of x, which is our initial condition. The method is usually defaulted to the fourth order method. And then T evaluation is optional, that you can specify the specific T's that you want to use. So for example, if we want to solve for y prime is equal to cosine x divided by y, this is a nonlinear ODE. We solve it numerically, then the function that we input will be the right-hand side of this equation if you write in terms of y prime is equal to something. So we input the right-hand side, and it will be a lambda function of x and y, the independent variable and the dependent variable of cosine x divided by y. And the T-span is the range that we want to evaluate it in. So the range domain we want to evaluate at is from 1 to 3. So we will input as a list 1, 3. Y of 0 is a list of initial values, but we usually only have one initial value. So here the initial value is 2. So we input a list of 2. And the t-span is optional, but if you want to evaluate at specific points, say 1,000 equidistant points within the range 1, 3, then you put a linspace command here. And you can look through the guided problem and the practice problem. The only thing different here is the SciPy integrate. So again, we define our initial condition, and when you copy and paste to different problem, be sure to check if your initial condition has changed. And then this is the ODE that we have, the left boundary, the right boundary, and our initial condition. Yes, this is
Okay.
tedious stuff.
Yeah.
So mine study have a piece and that was here. Payments.
Okay. So I choose what still need to make a new definition of archaic work. I just use my plot.
So you find dt with this thing.
Yeah,
So because it's input